Hello, today we are continuing in our A-level physics revision series looking at star classification, and we'll be covering the subjects of luminosity, apparent and absolute magnitude, intensity, standard candles, spectral classification, Wiens Law, Stefans Law, and the Hertzsprung Russell diagram. Luminosity is defined as the energy that is emitted from a star every second. So the total amount of energy that is radiated away in the form of electromagnetic radiation is the luminosity. And that is energy per second. Energy per second is, of course, the equivalent of power. And so luminosity will be given in watts, which is the unit of power. And just to give you some idea, the Sun, our own Sun, has a luminosity of 4 times 10 to the 26 watts, which means that's 4 times 10 to the 26 joules every second. So luminosity is total energy radiated every second. The intensity, however, is the, as it were, brightness that is perceived. So if this is the Earth, then there is some energy that will reach the Earth, but most won't. It will go off in a completely different direction. So it is just the energy that reaches the Earth that will determine the intensity of that star as perceived from the Earth. And the intensity that is perceived will depend on two things. Firstly, the luminosity. The greater the luminosity, the greater the intensity. But also it will depend on 1 over r squared, where r is the distance between that star and the Earth, because intensity falls off as the square of the distance. And this brings us to the concept of apparent magnitude, which is how bright things appear to be from Earth. And apparent magnitude is clearly also going to depend on the luminosity and the distance over which you are observing. So the brightest star in the sky is probably going to be one which is both highly luminous and near. Apparent magnitude is clearly going to be related to intensity, and we shall see how in a little while. 2,000 years ago, Hipparchus classified the brightness of stars on the following basis. To the brightest star he could see in the sky, he gave the classification 1. And the dimmest star he could see in the sky, he gave the classification 6. And all other stars in the sky were slotted in, according to their brightness, between the two. And so the magnitude of the brightness of the star was given by some number between 1 and 6. In the 19th century, this was formalised into what's called a logarithmic scale. What it means is that the brightness of a magnitude 1 star was regarded as being 100 times greater than the magnitude of a magnitude 6 star. So 1 is 100 times brighter than 6. But what it also means is that if 2 is x times greater than 1, and 3 is x times greater than 2, and 4 is x times greater than 3, and 5 is x times greater than 4, and 6 is x times greater than 5, then you've got, as it were, 1, 2, 3, 4, 5 lots of multiplication of x. In other words, x to the 5th is equal to 100, because if you multiply by x, by x, by x, by x, by x again, you've got 5 lots of x, so it's x to the 5th, and that will equal 100. And what that means is that x is very approximately 2.5. In other words, if you take 2.5 times 2.5 times 2.5 times 2.5 times 2.5, you get 100. But 2.5 is a rough estimate, it's not the precise. You need to do the 5th root of 100 to get the precise number. But the range 1 to 6 only applied to stars, and it only applied to stars that could be seen with the naked eye. Since then, the scale has been extended so that it still has the 1 to 6 range, but now it goes to 25, and that is for stars, certainly anything in this range will be stars that you cannot see with the naked eye, but which you can see with binoculars or telescopes. Obviously, once you get to 25, that is something like the dimmest item in the sky and can only be seen with a really powerful telescope. And every integral jump, so 6 to 7 or 7 to 8, you are going approximately 2.5 times dimmer. The scale also gets extended in this direction up to 0 and then -1, and in fact it goes all the way up to -25 and beyond. The Sun, for example, is beyond -25, somewhere here. The Moon is -12. Venus is -4. Now, how do we relate apparent magnitude to intensity? They are both the same sort of beast, but how are they different? Well, let's consider two stars that we observe from the Earth. Those two stars will have magnitudes MA and MB. That's stars A and B have a magnitude MA and a magnitude MB, and an intensity IA and an intensity IB as viewed from Earth. Now we know that the intensity of a magnitude 1 star is 100 times greater than the intensity of a magnitude 6 star. So the intensity of a magnitude 1 star divided by the intensity of a magnitude 6 star is 100. And by the analysis which I did up here to show that the intensity between any two adjacent integral values, 1 to 2, 2 to 3, 3 to 4, was 2.5, which is the fifth root of 100, what you can say is that the intensity of a 1 star divided by an intensity of a magnitude 2 star is equal to 100 to the 1/5, which is very approximately 2.5. The intensity of a magnitude 1 star divided by the intensity of a magnitude 3 star will equal 100 to the 2/5, which is the same as 100 to 3 minus 1 over 5. In other words, it's that number minus that number divided by 5. So more generally, the intensity of a star that has magnitude of magnitude B divided by a star which has an intensity magnitude A will be 100, that minus that, MA minus MB, divided by 5. And that's the general formula for looking at the intensity of a star that has magnitude B divided by the intensity of a star magnitude A, and that gives you. So now let's take logarithms to the base 10 on both sides. So log to the base 10 of IMB divided by IMA is equal to the logarithm to the base 10 of 100 MA minus MB divided by 5. And whenever you've got a logarithm, this term here, the exponent, can be brought down in front of the logarithm here as a multiplication. So that equals MA minus MB divided by 5 times the log to the base 10 of 100. But the log to the base 10 of 100 is of course simply 2. And so consequently, the log of IMB divided by the log of IMA is equal to this term here, which is 2 divided by 5 times magnitude A minus magnitude B. And that means if you rearrange that equation, you've got that MA minus MB is equal to, that's that term there, Bring this on the other side and you've got 5 over 2, because you reverse it when you take it to the other side, times this term here, which is the log to the base 10 of IMB divided by IMA. And that is a general term which relates the magnitude of two stars, A and B. This has a magnitude MA, this has a magnitude MB. And here you have the intensity of the star B, this is the intensity of the star A. And those two relate the magnitude difference to the intensities. Now, the absolute magnitude of a star is defined as the apparent magnitude if it were viewed from a distance of 10 parsecs. And a parsec is the equivalent of approximately 3.26 light years. And you can find out more about a parsec and why it is used in my video on parallax. So now let's consider two stars in the sky, A and B, and let's assume that they have the same luminosity. In other words, they are both generating precisely the same amount of energy per second. But of course, one may be nearer to us than the other, and so the intensities and indeed the magnitudes we will perceive will be different. And let us assume that A is r distance or r parsecs away, and that B is a distance 10 parsecs away. And as I've already said, if it's 10 parsecs away, then the magnitude will be the absolute magnitude, because that's how we define absolute magnitude. Now we know that the intensity perceived on Earth of the A star will be proportional to 1 over r squared, because intensity always falls off as the square of the distance. Whereas the intensity of the B star will be proportional to 1 over 10 squared, because 10 is the distance that the star is away. And since the constants of proportionality will be the same, that means that if you take IB divided by IA, that will equal r squared over 10 squared. Because we take that term divided by that term, we'll have r squared divided by 10 squared. And now we go back to the equation we derived before, which relates the apparent magnitude to the intensity of the stars. And we say that MA minus MB, which incidentally now this is the apparent magnitude, but this is the absolute magnitude because we know that star B is 10 parsecs away, is equal to 2.5, that's 5 over 2, times the logarithm to the base 10 of IB divided by IA. But IB divided by IA is r squared over 10 squared. So that's r over 10 all squared. And as before, you can always take the exponent down to this side here. So it's 2 multiplied by 2.5. So that becomes 5 times the log to the base 10 of r over 10, where r is the distance of the A star, and we know that B is 10 parsecs away. So if you know the absolute magnitude of one star, and you know the apparent magnitude of the other star, you can work out how far away star A is, because that's what r is, and that's now the only unknown in the equation. And what astronomers have done is to identify a group of stars which are called the Cepheid variable stars, sometimes called standard candles. The idea is that there are certain stars that, because of their nature and makeup, almost certainly have broadly the same luminosity. That is, they are emitting the same amount of energy. The distance of these stars, or the distance of the nearest of these stars, can be calculated using the method of parallax, for which you can see my separate video. So that means that if this is the Earth and this is a relatively nearby standard, so-called standard candle star, you can calculate the distance r by the method of parallax. You know what the apparent magnitude is, and you can therefore deduce from that what the absolute magnitude would be. And now, knowing the distance, which you've calculated by parallax, and the absolute magnitude which you've computed, you can look at another standard candle which is too far away to be measured by parallax, but you can measure its apparent magnitude, and using this formula here, so this now becomes star A and this is star B, and now using this formula here you can calculate the distance to this star. And now you've got distances calculated that go beyond what you could calculate by parallax. And finally, you can look at Hubble's constant, and I deal with this in a different video, where you look at the redshift of stars, maybe a long way away. You look at the redshift as the light is stretched out because the star is expanding. You look at the redshift, and what Hubble discovered was that the redshift the redshift was increased, or the shift towards red was increased, the faster that the star was receding, because the star is moving outwards. And what he showed was that the velocity of star is equal to Hubble's constant times its distance. So if you can find the redshift frequency, then you can calculate the velocity directly, and if you know Hubble's constant, you can calculate the distance of that star. And you can compute Hubble's constant by looking at these standard candles and their respective redshifts and the distances that you compute. In other words, you measure several standard candles, you find the distance to each one of the standard candles using this formula here and comparing it always with a close standard candle, the distance from which you've been able to compute by parallax. You then get a series of distances from this formula for all the standard candles in the sky at varying distances. You look at the redshift of each of these standard candles. That redshift enables you to calculate the respective velocity of each of them, and then you use this formula to compute. You know the velocity because that comes from the redshift. You know the distance because that's been computed in each case from this formula, and therefore you can calculate Hubble's constant. And now you can apply that to the much more distant stars, which are not standard candles. You simply look at the redshift. The redshift will give you the velocity. You already know Hubble's constant, so now you can calculate the distance. But of course, all of that critically depends on getting the distance to the nearby standard candle correct in the first place, and that is done using parallax. And as I explained in my video on parallax, that's very difficult because you are measuring very, very tiny angles and you have to do it very precisely. And if you make a slight mistake, you can get that distance wrong, and that means that your Hubble's constant will be seriously wrong. And that's precisely what happened in the early days. It's only as we have got more extensive equipment that we've got a better handle on Hubble's constant. Now, a star can be regarded as a black body, and in my video on black body radiation, I showed that if you plot the intensity of a black body against the wavelengths of the radiation, the electromagnetic radiation that it emitted, you might at first think that it should go up like this. That's called the ultraviolet catastrophe, because the ultraviolet is at this end, because ultraviolet is very short wavelength. This is wavelength increasing in this direction. You might think that the wavelength the intensity should increase dramatically once you get to the ultraviolet end, which would be bad news for ovens and electric fires, because it would mean we would all be subject to very dangerous levels of ultraviolet and even X-ray radiation. But in fact, what you find is that there's a peak, and then it falls off very sharply, so that you don't get very much intensity of the high end, the dangerous end of the electromagnetic radiation. And I explain why in my video on black bodies. But what I also showed was that if you plot the intensity of a black body against the wavelengths, you get a graph which shifts depending on the temperature, surface temperature of the black body. So that might be one temperature, this might be a hotter temperature, and this might be a hotter still temperature. This, let's say this one is 3000 degrees K, the next one is 4000 degrees K, and the next one is 5000 degrees Kelvin. And you'll notice that the peak wavelength moves to the left. Round about here will be the visible part of the spectrum. So by the time something gets about 4000 degrees Kelvin, you can actually see the light. Prior to that, it's infrared at the peak. But 4000, 5000 degrees, you are in the visible range of the electromagnetic spectrum. So the wavelength at the peak in each case, which is usually called lambda max, that is the wavelength at the peak of each curve, is defined by what's called Wiens Law, or sometimes called Wiens displacement law. And he said that if you take that wavelength of the maximum and multiply it by the temperature, which is in either 3400 or 5000, you get a constant, which is 0.00029 meter Kelvin. And the curious terms, of course, have to balance this. Wavelength is measured in meters, temperature is measured in degrees Kelvin. So that is what's called Wiens Law, and it simply enables you to calculate, if you know what the surface temperature of the black body is, then you can calculate where the maximum of the intensity of wavelength will be. Now, luminosity, if we take a star, and we said that luminosity is the total amount of energy that is being radiated out at any one time, you'll be able to see that that radiation, that intensity of radiation, will depend on the temperature at the surface and also on the surface area. The bigger the surface area, the more scope there is to pump out radiation. And that brings us to another law. This is Stefans Law, which says that the luminosity of a star is equal to sigma, which is Stefan's constant, multiplied by the surface area of the star, multiplied by the temperature to the power 4. And Stefan's constant is 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the degree 4th. And that is obvious because that has to balance this with this. Luminosity is measured in watts, area is measured in meters squared, and temperature to the power 4th is measured in Kelvin to the power 4th. Now all that energy, that luminosity that is coming out from that star, let's represent that star as a point, the energy is coming out in all directions. And when we get to a distance, let's say r away from the star, so I'm now going to draw a shell of radius r, and let us suppose that the Earth occupies a point on that shell. All this luminosity is coming out and, as it were, hitting that shell. I'm not suggesting it's a physical shell, I'm just drawing a shell, as it were, around the star. That intensity will, as it were, be spread out, and it will be spread out over the whole of the surface area of that sphere. And so the intensity that hits any point on that sphere will equal the luminosity divided by the surface area of the sphere, which is 4 pi r squared. And now we've got a relationship between the perceived intensity at a point and the luminosity of the star, which is the total energy that is being radiated per second. And now we move on to the spectral classification of stars, which will be used to determine the temperature, the surface temperature of the stars. We know that spectral lines are determined, and I've shown this in another video, by the action of electrons being, as it were, given energy and promoted into outer shells. So if you have, since stars are mainly made up of hydrogen, you will have just one electron in a hydrogen atom. Here is the hydrogen nucleus, which will be, of course, one proton. Here is an electron, as it were, orbiting that nucleus. And if that electron gets energy, it will be, as it were, promoted into a higher orbit, electron orbit. But having got there, it will then want to fall back to its original orbit. It will want to go to a lower energy level. It will do that, but it will give off energy as it does so. And that energy will be given off in the form of a photon. And the photon's energy will be given by Planck's constant times nu, where nu is the frequency of that photon. So an electron falling from that level to that level gives off a precise amount of energy, which is the energy difference between the two orbitals, and that energy converts into a precise frequency, which is why when you look at a piece of film, you will see a very precise spectral line. But of course there are lots of energy levels. If this is the ground state, then this might be the first excited state, the second excited state, the third excited state, and so on. And an electron here could go up here and come back down again, or it could go up here and come back down again, or it could indeed go up here but only come back here temporarily and then later fall. It all depends on how the electron is performing, and that depends on the energy that the star has. Now, we discussed in another video that I did what's called the Balmer series. And this is the series where the electron starts and finishes in the n equals 2 shell, not the ground state, which is n equals 1. There's enough energy for electrons already to be in the n equals 2 shell. And then they go up into a higher shell and come back down again. And what we showed was that the hydrogen visible spectrum, there are 4 lines. 1, 2, 3, 4. They're actually differently spaced than that. But what they represent is the transition from either 6 down to 2, from 5 to 2, from 4 to 2, and from 3 to 2. So the electron goes up to, let's say, energy level 6 and comes back down again. That will then give off, of course, a photon, and that will be this one. If instead the electron goes up to energy level 5 and comes back down again, it will emit a photon of a different frequency because the energy difference will be different. And we've already shown that energy equals E equals h nu. And so you will get then that spectral line. Now the temperature of the star determines the amount of energy that you've got to get these electrons promoted up in the first place. So the hotter the star, the greater will be the intensity of the spectral lines which represent the greater energy. And as a consequence of observing spectral lines and their relative intensity, which gives us the measure of the temperatures of the star, the stars have been classified into the following categories, starting with the very hottest, O, B, A, F, G, K, M, where O has a surface temperature of about 50,000 degrees Kelvin and M has a surface temperature of about 3,000 Kelvin. Now, like most exam students, you want a mnemonic that will help you to remember this order, and the standard politically incorrect mnemonic is "Oh, be a fine girl, kiss me," or if you prefer, "Oh, be a fine gentleman, kiss me." It's just a means of remembering the order of the letters. Why are they in that order? Largely historical. There were several means of classification. They were all amalgamated. Some of them were dropped, and you ended up with this curious mixture of letters. And just to make it more awkward, each of the letters is further subdivided into categories 1 to 10. So you can have an O1 up to an O10 star, a B1 to B10, and so on. The Sun, our very own Sun, is category G2. So you can see that it is at the cool end of the spectrum. It's about 5,800 degrees Kelvin as its surface temperature. Now, two gentlemen by the name of Hertzsprung and Russell are very famous for producing their diagram. It's called the Hertzsprung Russell diagram, where they look at stars in the sky and they plot them. So we take the OBA fine girl kiss me range of temperatures. So this is now measuring temperatures from 50,000 degrees K to 3,000 degrees K. So it's important to notice that the temperature scale moves upwards in that direction on this graph, and plot against that the absolute magnitude of the star that you have to calculate. And so, and the absolute magnitude in this case goes upwards, so it's brighter as you go up the scale. So a star here will be a very, very hot star because it's O, and it will also be a very, very, well, absolute bright. It may not appear to be very bright because it might be a long way away, but its absolute magnitude will be large. And so this is a very hot and very bright star. Whereas if you go to the other end, here you have got a very cold star, or cool, because it's not 3,000 degrees K is not cold, but it's cold by comparison, and dim. And what they found was when they plotted stars, temperatures against absolute magnitudes, they got pretty much a straight line. And that's called the main sequence of stars. Most stars fall somewhere on that line. The hotter they are, the higher the absolute magnitude. And the Sun, our own Sun, is indeed on the main sequence, and it's in this range here. And all the stars that are on the main sequence are broadly at the stage where they are converting hydrogen into helium. That's all they do. What Hertzsprung and Russell found was that there was another group of stars up here in this category here. Now, if we look, what we find is that they have a high absolute magnitude, but a relatively low surface temperature. And they are called the red giants. And what was discovered was that they have expanded massively, so that's why they have an apparent or a high absolute magnitude, but they are cooling because they are getting towards the end of their life. This is the stage where the higher elements up to iron are being manufactured. Hertzsprung and Russell also found that there was another group of stars in this region here. Now this means that they are very hot. They are at the 50,000 degrees end, but very low absolute magnitude. And these are called white dwarfs. And these definitely are at the end of their life. What has happened is that in many cases the red giant has exploded in the form of a supernova, and that's the point at which all the elements above iron are made. I cover this in another of my videos. And then what's left of that star, all the nuclear processes have now finished. All you're left with is a very, very hot star, which is why it's hot, but it's very, very small, so its absolute magnitude is small. And all that will happen to that white star is it will cool down. It will take potentially billions of years to do that, but eventually it will cool down so far that it no longer emits electromagnetic radiation in the visible range, and you won't be able to see it anymore. But if we briefly go back to Stefans Law, which is that the luminosity is equal to Stefan's constant times the surface area times the temperature to the power fourth, luminosity is dependent upon surface area and temperature, keep that thought, then what you can conclude is that if you've got high luminosity and low temperature, that must mean that you've got a large area. And if you've got low luminosity and high temperature, then that must mean that you've got a small surface area. And that's exactly what you've got here on the red giant. You've got a high luminosity but a low temperature, and that means you must have a large surface area. That's why they're called red giants. Here with the white dwarfs, you've got a low luminosity, a high temperature, therefore you must have a small surface area, and that's why they're called white dwarfs. X by X again, you've got 5 lots of X, so it's X to the 5th, and that will equal 100. And what that means is that X is very approximately 2.5. In other words, if you take 2.5 times 2.5 times 2.5 times 2.5 times 2.5, you get 100. But 2.5 is a rough estimate, it's not the precise. You need to do the 5th root of 100 to get the precise number. But the range 1 to 6 only applied to stars, and it only applied to stars that could be seen with the naked eye. Since then, the scale has been extended so that it still has the 1 to 6 range, but now it goes to 25, and that is for stars, certainly anything in this range will be stars that you cannot see with the naked eye, but which you can see with binoculars or telescopes. Obviously 6 watts, which means that's 4 times 10 to the 26 joules every second. So luminosity is total energy radiated every second. The intensity, however, is the, as it were, brightness that is perceived. So if this is the Earth, then there is some energy that will reach the Earth, but most won't. It will go off in a completely different direction. So it is just the energy that reaches the Earth that will determine the intensity of that star as perceived from the Earth. And the intensity that is perceived will depend on 2 things. Firstly, the luminosity. The greater the luminosity, the greater the intensity. But also it will depend on 1 over r squared, where r is the distance between that star and the Earth, because intensity falls off as the star was given by some number between 1 and 6. In the 19th century, this was formalised into what's called a logarithmic scale. What it means is that the brightness of a magnitude 1 star was regarded as being 100 times greater than the magnitude of a magnitude 6 star. So 1 is 100 times brighter than 6. But what it also means is that if 2 is x times greater than 1, and 3 is x times greater than 2, and 4 is x times greater than 3, and 5 is x times greater than 4, and 6 is x times greater than 5, then you've got, as it were, 1, 2, 3, 4, 5 lots of multiplication of x. In other words, x to the 5th is equal to 100, because if you multiply by x by x by x square of the distance. And this brings us to the concept of apparent magnitude, which is how bright things appear to be from Earth. And apparent magnitude is clearly also going to depend on the luminosity and the distance over which you are observing. So the brightest star in the sky is probably going to be one which is both highly luminous and near. Apparent magnitude is clearly going to be related to intensity, and we shall see how in a little while. 2,000 years ago, Hipparchus classified the brightness of stars on the following basis. To the brightest star he could see in the sky, he gave the classification 1. And the dimmest star he could see in the sky, he gave the classification 6. And all other stars in the sky were slotted in, according to their brightness, between the two. And so the magnitude of the brightness of the... Hello, today we are continuing in our A-level physics revision series looking at star classification, and we'll be covering the subjects of luminosity, apparent and absolute magnitude, intensity, standard candles, spectral classification, Wiens Law, Stefans Law, and the Hertzsprung Russell diagram. Luminosity is defined as the energy that is emitted from a star every second. So the total amount of energy that is radiated away in the form of electromagnetic radiation is the luminosity. And that is energy per second. Energy per second is, of course, the equivalent of power. And so luminosity will be given in watts, which is the unit of power. And just to give you some idea, the Sun, our own Sun, has a luminosity of 4 times 10 to the 23